Hello everyone, this is Marwan Omar and my presentation today is on a topic called VulDefend, a novel technique based on pattern exploiting training for defending software vulnerabilities using large language models. Here's the outline of the presentation. We will start with a problem statement, then we will talk about language models and how we can deploy them and utilize them for detecting software vulnerabilities, which is a huge issue for software programs. And then we will talk about how we can use specifically transformer-based architectures to detect software vulnerability. We will talk about our systematic framework, the pattern exploiting training. We will then move on to discuss our results, and we will wrap up with a conclusion. So here's the problem statement. Software is an integral part of most computing devices. Just about any computing device will have software installed in it. The problem is that adversaries exploit these software vulnerabilities to gain unauthorized access and control over systems for the sake of stealing data or modifying sensitive data and private data for their benefit. Therefore, detecting and patching these software vulnerabilities is an important aspect to secure the products from adversaries. On the right side of the slide, we show some of the examples of software vulnerabilities that have led to cyber attacks. We can see Apple zero-day wows continue, Microsoft Exchange server targeted with zero-day vulnerabilities, Zoom patches zero-day vulnerabilities in Windows 7, code vulnerability failures in manufacturing on display in Toyota supply chain attack, NVIDIA Shield TV up to 8.21 buffer overflow, Apple macOS used a file buffer overflow, Facebook WhatsApp on Android video stream buffer overflow. So these are just some of the highlights from the news and from the media about different software vulnerabilities impacting high-tech companies, including Apple, Microsoft, Zoom, etc. So software vulnerabilities are a huge issue targeting just about every industry. Here is the research problem that motivated our research and drove our research. Given the source code of a target program, meaning the software application here, the question is, how can we determine whether or not the target program is vulnerable, and if so, where are the vulnerabilities? Without asking human experts to manually define features, without incurring a high false negative rate or false positive rate. As we all know, false positive and false negative are huge considerations when we design a software vulnerability detection system, because you want our system to have a low false positive and a low false negative rate. And we do not want to have humans in the loop. So we want to minimize the manual labor associated with detecting software vulnerabilities. Automatic software vulnerability detection. Automatic detection of software vulnerabilities is an important research area. So we also have static vulnerability detection tools and studies such as Flaw Finder, RATS, Coverity, Fortify, Cobot, Redebug, Buddy in 2017, VulDefend 2016. So, and there are more and more research studies as well as products out there for detecting software vulnerabilities in an automatic manner, meaning without using humans, without relying on humans to detect these software vulnerabilities. Drawbacks of existing approaches: first, imposing intense labor of human experts. So humans have to be in the loop, and so we need domain expertise, domain knowledge, and the humans who are the experts in that domain, they need to manually define the features. Second problem or drawback or limitation is the high false negative rates. So we have two of the most recent vulnerability detection systems, VulDefend. False negative rate was 18.2 for Apache HTTPD 2.4.23. We also have VulDefend. False negative rate is 38% with respect to 455 vulnerability samples. So these are just some of the studies. There are more and more recent ones like VulBerta, VulDetect, and many other most recent studies that rely on using language models to automatically detect software vulnerabilities. Most of them just scale to C and C++ applications. Let's now talk about some of the challenges for detecting vulnerabilities in software applications. We know that software vulnerabilities can be costly and they can be prevalent, as we talked about, but it is hard to detect and prevent them. We have the static analysis tool, which have been proposed as we spoke about them, but they are still inaccurate because they are time-consuming and they might suffer from false positive rates. Within a project consists of millions of lines of code, security analysts may be required to spend a huge amount of time and effort in order to locate the exact vulnerability, and that's a huge challenge. In this slide, we are going to show some of the examples of software vulnerabilities. On my left side of the slide, this code snippet is a vulnerable code with buffer overflow. On my right side with a green highlighted text, it's a non-vulnerable. On my left, it's vulnerable to buffer overflow because, as you can see here, highlighted in red, data equals character times null allocation 50 times size of character. And then the source is 100. So this is vulnerable to buffer overflow attacks. Buffer overflow vulnerability could lead to attacks. So buffer overflows are considered some of the most dreaded vulnerabilities for software applications. Here is another example of software vulnerability. On my left side, we have vulnerable code with resource management error, RME. And on my right side, highlighted in green, this is not vulnerable because we're deleting the data. However, on the left side, that code is bad because the data needs to be released or deleted. So these are just two of the examples on vulnerable and non-vulnerable code. And this is what this project is trying to do, detect software vulnerabilities using language models and pattern exploiting training. In this slide, we will talk about how we can use machine learning to detect software vulnerabilities. So machine learning has been used extensively in the past to find and detect software vulnerabilities. We have a piece of code. We can deploy a machine learning system, supervised learning system, maybe even launch your LSTM system, RNN, etc., to detect whether a piece of code is vulnerable or non-vulnerable. So this becomes a traditional classification test. So the green arrow, that means it's not vulnerable, the piece of code that you have on the left. And the red X and circle is vulnerable. So it's a classification task. It's a binary classification task. So machine learning algorithm, a learning algorithm can be utilized to classify software into vulnerable versus non-vulnerable. Here, underneath that, we can use language models such as BERT, Roberta, etc. to detect software vulnerabilities in a more efficient manner. And this is part of this topic's presentation. So in this slide, we will talk about why deep learning and NLP, natural language processing systems, are better than traditional ML for detecting software vulnerability. There are several reasons. First of all, the ability to process unstructured data. We know that traditional ML relies on structured data, while deep learning and NLP are designed to handle unstructured data, text, making them more efficient at processing natural language text data related to software vulnerabilities, because we treat the source code as input text. The second reason is better feature extraction. Deep learning models can automatically learn relevant features from raw input data, eliminating the need for feature engineering. This enables them to uncover complex patterns and relationships in the data that traditional ML algorithms may not be able to detect. Also, better performance. Deep learning models have been shown to outperform traditional ML algorithms in a wide range of NLP tasks, including test classification, sentiment analysis, etc., question answering, etc. This allows software vulnerability detection systems to achieve high accuracy and better performance. Another reason is adaptability. Deep learning models can be easily adapted to new and changing data sets, allowing them to learn from new software vulnerabilities as they are discovered. This is especially important in the rapidly evolving field of cybersecurity. In this slide, we are looking at transform-based language models and how we can use them to detect software vulnerabilities. So transform-based models are state-of-the-art models in NLP. We can extend the use of these models beyond NLP tasks through the process formerly known as transfer learning. Examples are BERT, DistilBERT, CodeBERT, GPT-2, Megatron-BERT, and Megatron GPT-2. So here we can simply utilize and leverage the power of language models to detect software vulnerabilities. Here is some information about our systematic framework. For data translation, we use code gadgets and their extractions. For data preparation, we do data cleaning by removing the duplicate code gadgets and the same gadgets with conflicting labels. For data pre-processing, replacing the user-defined function name and user-assigned variable names. For data partitioning, we partition them into groups, and then word embeddings, we tokenize and embed each token. Here is our methodology and the proposed approach. So the proposed approach for vulnerability detection in source code using pattern exploiting training and closed style questions. So you start with C or C++ code, and then you convert to code gadgets. Then you convert the code gadgets to tokens, convert the tokens into embeddings, and feed the embeddings into the language model and apply the pattern exploiting training and closed-style questions. So in the pre-processing stage, the raw source code data is transformed into a format that can be used for training the language model. This typically involves the following steps, which are also depicted schematically in figure 1 as we saw. So tokenization, the source code is first divided into individual tokens, such as keywords, variables, and punctuation marks. Then we normalize. Normalization, the tokens are then transformed into normalized form to ensure consistency in data. For example, all function names may be converted to lowercase. Labeling, each token is then labeled according to its role in the code. This can include labeling tokens as variables, keywords, function names, etc. And then close generation, the pre-processed tokens are then used to generate closed-style questions, which replace a portion of the code with a mark with a mask token and ask the model to predict the missing information. In this slide, we're talking about pattern exploiting training. The intuition behind using pattern exploited training to reformulate input samples into closed-style questions is semi-supervised learning setting. Leverage the patterns in the input data to generate new training examples, which can be used to fine-tune machine learning models for vulnerability detection. This approach can be especially useful in situations where labeled data is limited, as it allows the model to learn from the patterns in the data without having to rely solely on annotated examples. Let's consider a training data set D consisting of n input and output pairs, where each input xi is a piece of code and the corresponding output y is a label indicating whether or not the code contains a vulnerability. We want to use pattern exploiting training to reformulate these inputs into closed-style phrases for vulnerability detection. To do this, we first identify a set of key patterns in the input data. Each key pattern, Pj, is associated with a set of indices, such that for each index xi contains Pj. We then generate a new set of inputs by masking some of the information in each input, such that xi equals close xi pi for some Pj belongs to P. The close function is defined as close xi Pj equals xi with Pj masked. Imagine that we are tasked with detecting vulnerabilities in function calls given a benchmark dataset such as reveal. In the context of function calls in source code, the fundamental patterns are likely to include the names of functions being called, the types of arguments being passed, and these functions, and the potential security implications of these calls. By reformulating the input samples into closed-style questions where some of this information is masked, the model can learn to predict the missing information. We then train a machine learning model F on the reformulated inputs and the corresponding outputs Y to predict the masked information. Given a new input, the model can make a prediction by first transforming the xnew into a closed-style phrase and then making a prediction based on xnew. Mathematically, this can be expressed as x equals x close xi pi for I belongs to 1 to n. The cross-entropy loss function is commonly used as the loss function for training machine learning models in supervised learning settings. In the context of pattern exploiting training for vulnerability detection, the cross-entropy loss can be used to measure the difference between the predicted labels and the actual labels. Our framework is designed to automatically detect software vulnerabilities, security vulnerabilities in software source code, as shown in Figure 1. VulDefend uses the fine-tuned BERT model to detect the vectors corresponding to the vulnerable code gadgets generated from a target source. Our BERT model receives an input as a long character string containing a C file. In the next step, a tokenizer breaks the string into words and subwords. It's critical to note that syntax characters such as periods, semicolons, parentheses, and bracket periods are considered separate words. Afterward, the encoder encodes the words into vector representations. These vector representations of words are either fed token by token into the model or in large chunks. Here we talk about our data sets. The Divine dataset, initially presented by previous researchers, it presents a real-world example of a dataset designed for software vulnerability detection, comprised of function-level C, C++ source code, sourced from two popular open-source software projects. Divine dataset presents a carefully created set of examples. The labeling and verifications of the examples within this dataset was conducted through a two-round process by a team of experienced security researchers, ensuring the accuracy and reliability of the data. Next is the SAR dataset, Software Assurance Reference Dataset. It's a dataset that provides information and resources related to software assurance and security. It's aimed at providing a comprehensive collection of real-world, publicly disclosed vulnerabilities and their associated source code. The SAR dataset includes information on various types of vulnerabilities such as buffer overflow, cross-site scripting, and SQL injection. The database is regularly updated with new vulnerabilities and is widely used in academia and industry for evaluating the effectiveness of software assurance and security techniques. Then we have the Reveal dataset, which serves as a response to the limitations of existing datasets in the field of software vulnerability detection. The limitations are primarily characterized by high levels of data duplication and unrealistic distribution of vulnerable classes. We have the D2A dataset, which is a comprehensive real-world vulnerability detection dataset introduced by the IBM research team. This dataset comprises a selection of popular open source software projects, including FM, PIG, HTTPD, etc. The dataset was created through the application of a differential analysis technique, which was utilized to label issues reported by static analysis tools. We now talk about the results. For each of the three training runs, we provide the mean accuracy and the standard deviation. The first two lines, L1, L2 of the table, display the performance of the unsupervised techniques with the maximum average results across all data sets on the test set being reported. The considerable difference between both rows highlights the need to account for the fact that without examining the test set, there is no way to assess which method performs well. So here are some of our results. Training examples 0, 15, 60, 200, 1000, using both unsupervised and supervised and pattern exploiting training on all the different 4 data sets. Comparison of VulDefend, VulDefend, PET, and IPET. Unlike VulDefend and VulDefend, where large development sets are employed to optimize the number of training steps, we use several iterations of both approaches directly on the test set and report the best results obtained. PET and IPET exhibit significantly superior performance on all datasets compared to the 2 alternative methods. This outcome unequivocally underscores the advantage of incorporating knowledge distillation. The comparison results presented in the table 2 reveal that PET and IPET outperform VulDefend and VulDefend across data sets, indicating the advantage again of incorporating knowledge distillation and transfer learning. So here are the results of the comparison between VulDefend, PET, and IPET. Comparative analysis. The comparison between PET and the state-of-the-art techniques for detecting software vulnerabilities, VulDefend and VulDefend, is a significant aspect of this study. While PET requires the identification of patterns to express a given task, VulDefend and VulDefend rely on supervised training using thousands of label examples to train a language model. Comparison is based on BERT-based, as VulDefend and VulDefend are specifically tailored for a 12-layer transformer. In this slide, we talk about supplemental language modeling. We analyze the impact of the supplemental language modeling task on the performance of PET. Figure 2 illustrates the performance gains resulting from the inclusion of the language model task across 4 different training set sizes. The results indicate that the auxiliary task provides significant benefits when the training set is limited to only 15 examples. As the amount of training data increases, the importance of the auxiliary task diminishes, and in some cases, it may even lead to a decrease in performance. However, we find that the language modeling task consistently improves performance for the defined data set. So this is figure 2. The inclusion of additional language modeling during training resulted in improvements in accuracy for text using supplement language modeling. So there are some limitations of traditional approaches. Distillation knowledge of individual models into a single classifier may hinder learning from each other. Some patterns may perform much worse than others, leading to mislabeled examples in final training sets. So the IPET approach leverages an iterative approach called IPET. It trains multiple generations of models on progressively larger data sets and expands original data set T by adding label examples into data. Here are some limitations about using flow-style phrases in PET for vulnerability detection. Data limitations, we have generalization issues, model limitations, domain-specific limitations, interpretability limitations. Vision for addressing these limitations is use parameter sharing and reformers. So in conclusion, there's a potential for closed-style phrases in PET for vulnerability detection to improve the accuracy and efficiency of vulnerability detection source code. Our future research and development will focus on devising new techniques based on parameter sharing and utilizing innovative language models such as GPT and reformers. This is the end of the presentation. Thank you.